Okay, let's do a check for understanding walkthrough. So in this question, we've got a rational function with a 10th degree numerator and some unknown function g of x in the denominator. And I want to know what could g of x look like, which would make it true that the limit of this function as x approaches infinity equals 0. So first, remember what that means. What we're saying here is that the y values, as x gets really big, are getting closer and closer to 0, which is just another way of saying there's a horizontal asymptote at 0. So we don't know what this function looks like sort of in the middle, but we do know that as the function's getting bigger and bigger, the y values are approaching 0. And it doesn't have to be from the top. It could be from the bottom, or it could be oscillating, but the point is they're getting closer to 0. Okay, so what would be an example of a function that does that? So we've got 5x to the 10th plus some smaller degree terms divided by something. Okay, so you know from our discussion of horizontal asymptotes that if this was like 5x to the 10th, then these are the two dominating terms. And so this function, when x is very large, behaves as if it's just 5 divided by 5, which is 1. So if the bottom function had a highest degree term of 5x to the 10th, which is what some people put, that would imply it had a horizontal asymptote at y equals 1 and not at y equals 0. Okay, so what if it was like a really big coefficient, x to the 10th? This doesn't really work either, because if I look at the two dominating terms, these would simplify as 5 over 999. And so that would give me a horizontal asymptote at y equals 5 over 999, but still not at 0. So the question is, how can we make sure that as x gets really big, my function is approaching y values of 0? And an easy answer is, as long as the degree of the denominator is a higher degree than the numerator. And it sort of doesn't matter what the coefficients are, because if you look at the two dominating terms, these are going to simplify to be like some number divided by an increasing function, such as x. And so we know that as x gets really big, this approaches 0. What we're saying, like when we say that our function is approximately equal to this, what that means is that the y values of our original function are very close to these y values for really big values of x. So if this thing is approaching 0 and our thing is very close to that thing, it also means that our original thing has y values that are approaching 0. So it doesn't have to be x to the 11th. You could write any polynomial you want that's degree larger than 10, and that would work as an answer. Okay, what about this one? So we've got x squared minus 9 divided by x minus 3 and x squared plus 9 divided by x minus 3. So these are very similar to each other. And it says find the following limits. Find the limit as x approaches 3 of f and x approaches 3 of g. So I want to know, so like obviously as x is approaching 3, we've got some kind of discontinuity happening. But the question is which? So let's try and sketch these. If I've got the f function, which is x squared minus 9 over x minus 3, the numerator factors as x plus 3 and x minus 3. And so here you'll notice, so the numerator factors. And so here you'll notice that these two terms divide each other to be 1. So what that means is that this function actually looks like the line x plus 3, except that there's a hole right here at x equals 3. Because if I plug in x equals 3 to the original function, you get 0 over 0, which is this removable discontinuity. Okay, so that was f. Let's look at g. So for g, I've got x squared plus 9 over x minus 3. For this one, you can't factor the numerator at all. So if I plug in x equals 3, I end up getting 9 plus 9 is 18 divided by 0. And so that's characteristic of a vertical asymptote at x equals 3. Let me see. So if I have so it would be like this. Oh, is that true? Hold on. Okay, so sorry for the interruption. So we don't actually really care what this function looks like at intervals that are not close to x equals 3, but what we know for certain is that there's a vertical asymptote at x equals 3. Okay, so now that we've sort of visualized what do these functions look like right around the point where we're asking about limits. So here we're asking what's the limit as x approaches 3 of f of x. A lot of people just said 3 because I think you weren't really thinking very carefully about what is this actually asking. What this is actually saying is when x gets very close to 3, what do the y values get very close to? And so as x gets very close to 3, the y values are getting close to where this hole is. But where's the hole? Like imagine that we divided out the x minus 3 factors. If I plug in x equals 3 here, you see that 3 plus 3 is 6. So the hole is at 6, so that means the limit is 6. So that was a little bit tricky because you had to think about kind of what is this question actually asking, and you had to realize that you can remove the discontinuity by actually performing that simplification. In this case, limit x approaches 3 of g of x equals does not exist because from the right-hand side, we're increasing without bound. From the left-hand side, we're decreasing without bound. And you wouldn't actually have to think that hard about it. Like as soon as you've got a vertical asymptote, you know that the limit doesn't exist. So that would be a solution to that one. So here we've got a polynomial has a bunch of roots, another polynomial has a bunch of roots, and we want to know where are all the vertical asymptotes when you divide them. So like let's just do an example. If I have like x minus 2, x plus 3, and here I've got x minus 2, x plus 5. So here, this one the numerator has roots at 2 and negative 3. The denominator has roots at 2 and negative 5. So what does it mean if the numerator and the denominator, what does it mean if the numerator and the denominator both have the same root? If both functions on the top and the bottom have the same root, then that means that each polynomial has a factor which is the same and can be divided. And so that means that you're going to have some removable discontinuities there. What about when the denominator has a root that the numerator doesn't have? In that case, you've got a vertical asymptote. What does it mean when your numerator has a root that your denominator doesn't have? This would be a 0 of your entire function. Because if you imagine plugging in x equals negative 3, you'll end up getting 0 divided by something that's not 0. So if you have 0 divided by any non-zero number, that's just equal to 0, which is the same thing as a root of your original function. So the question you want to ask yourself is, are there shared roots between the numerator and the denominator, or is it one or the other? And like, what does each of those situations mean? So here to look at the problem, all right, so we want to know where there are vertical asymptotes. So vertical asymptotes are going to happen whenever there's roots in the denominator that aren't shared by the numerator. So looks like it's going to happen at 4 and 20, and that's it. So it should be, well, I guess they don't have numbers here, but whichever one, yeah, at x equals 4 and x equals 20 only would be the answer. Okay, cool. So what do A and B have to be so that it's got one vertical asymptote located at x equals 5? Let's solve that one. So if I want one vertical asymptote at x equals 5, what that means is that, hold on. So here I've got, in the denominator, I've got roots at x equals 3 and x equals 1. So that means that my numerator needs those same roots to make x equals 3 and x equal 1 be removable discontinuities instead of vertical asymptotes. So here I've got a minus x and I've got x minus b. Okay, so like one of these, all right, so let's set b to be a value so that 1 is a root in the numerator. So like if b equals 1, now that problem's solved because these would divide each other. What about this one? So I want to make sure that this term is like has an a value, where if x equals 3, then a minus x is going to equal 0. So like hopefully you can see just by inspection that if a equals 3, that does it. A different thing you could do is solve for a. You could say a minus 3, I want it to equal 0, therefore a equals 3, and so it's like an algebraic equation. Another way you could do it is factor out a negative sign. So a minus x is the same thing as the opposite of x minus a. So if you rewrote it that way, now it's really clear that a could be 3. So 3 different ways to think about it. Okay, so in any case, a and b should have the values of 1 and 3. Okay, let's do another one. Oops. So that answer I just selected was wrong. The one I said verbally is correct. Okay, so what is the horizontal asymptote of this? So let's look at the dominating terms. So 4x squared minus 2x plus 1 divided by 3x squared minus 71. So this function is approximately equal to the two dominating terms, only for very large values of x. So for x much greater than 0. This simplifies to be 4/3. So that tells me there's a horizontal asymptote at 4/3. It's nice when there's a simpler one. Okay, so now same deal as that other one. So I've got a bunch of roots in the numerator, a bunch of roots in the denominator. This time I want to know where are the removable discontinuities. So if you remember from our discussion before, the removable discontinuities happen whenever you have the same root in the numerator and the denominator. So in this case, f and g have a common root of 10, and that's it. So there's only a removable discontinuity at 10. And that's the answer to that one. Okay, cool. I hope that this was helpful. You can also tell that I'm really trying to come up with questions that will test your understanding of the underlying concepts, but the actual steps that you use to solve the problem might be different. And that's, I hope you've experienced, like kind of normal for this class. So definitely understand the steps that I took for these problems. But you also want to think about like, what's the important idea at work in the problem? What are different ways that that idea could look? Like in these ones, I just said there's a polynomial with certain roots. In the homework problems, I gave you graphs of f and g. And from the graphs, you figure out what are the roots and then answer the question. We've done it with equations. So I'm trying to show different ways of seeing the same idea. And your task is to be able to recognize, aha, here's the important information that I need to answer the question. And then figure out like sort of where do you get the information from and what do you need to do with it. And that's going to be a little bit different than just memorizing some steps. So good luck. Please message me if you have questions. And I hope you guys do great on the quiz.